Thank you for joining us on this webinar on performing sequential stepper moves. The presentation itself is roughly about 20 minutes, and as usual, if you have any questions, feel free to put them in at any point and we can get to those at the end. So let's get going.
Welcome to today's tutorial. Let's get started. Here's our agenda for today. Today we're looking at performing sequential stepper moves. First, we'll talk about similar content we covered previously, and then we'll do a quick review of step and direction control. Next, we'll talk about commanding a single move, and then we'll go into detail on our topic, which is using a user-defined function block to execute a series of moves. We'll create that UDFB for executing a single move, and then we'll string them together using different techniques to execute a sequence of moves. We'll have demonstrations throughout, and as always we'll finish with a Q&A session. Around a year ago, we released a video called Integrating Stepper Motors with the Horner OCS, which we would recommend that you watch if you've not seen it already. In that video, we went through what is the stepper motor, the advantages and disadvantages of steppers, we compare them with servos, and we look at the trapezoidal move profile. We also talked about using step and direction control, and then we did a hands-on demo. So let's do a quick review of step and direction control. Stepper motors are positioning motors that have several advantages. First, they have a low cost. They have good performance when used in open loop operation, which is how they're usually used. That's partly because it has good low speed torque and good holding torque. Today, you can control a stepper motor over a network with CAN-open or Modbus TCP, for example. Traditionally, stepper motors have been controlled with step and direction signals, however. With step and direction, you have an indexer component, and the OCS can act as a stepper indexer. That indexer component sends a DC pulse train, where each pulse represents a position increment. For instance, every pulse could tell the motor to rotate 1/400th of a revolution, for example. The stepper drive converts that pulse train signal to motor current signals that will cause the motor rotor to be positioned. Now let's talk about commanding a single move. First, let's talk about the trapezoidal move profile, which is shown in that diagram. On the right, the OCS will be commanding a total distance to be traveled. Think of the rotor turning as a linear distance. So think, how far are we telling that rotor to travel, and we'll give it that distance in pulses. That's split into how many pulses we're going to send while accelerating, how many pulses will we send while running at full speed, and how many pulses will we send when we are decelerating. What about the speed or the frequency at which those pulses are sent out? Well, here you have a starting velocity, which is the number of pulses per second for the pulse train when motion begins. Then you have your running velocity, which is the maximum number of pulses per second that is achieved during the move. So those 5 parameters we mentioned are shown on the left, and they need to be specified in your Cscape program. They are all mapped to real-world I/O points in the high-speed counter/high-speed output functionality in an XL series, XL prime, or X5 unit. If you're using the 2-counter mode in an XL series unit, you can have up to 2 stepper motors that you drive. Stepper number 1 has real-world I/O allocation as shown in the 3rd column of the chart, and stepper number 2 has the allocation as shown in the 4th column, and all those parameters are all double integers in the application. Next, you have to control and monitor some digital bits that are also allocated to real-world I/O in order to trigger the motion. For stepper number 1, you're looking at Q1. So you need to map one of your Boolean variables to %Q1, which will be the variable you manipulate to initiate motion. You also need to monitor status coming back from the stepper in the OCS. That's coming through 2 bits for stepper number 1, %I1617 and %I1618. That first bit is a ready/done bit that tells you when the stepper function is ready to go and when it's completed the move or is done. The second bit is an error bit that tells you that the parameters you've set for your move are illegal and won't work, or that your move was interrupted. Let's look at this in spreadsheet form before we begin our first demo. We'll start by setting the move parameters, which are the AQs for our distance and our velocities, and then we set the direction output. For stepper number 1 and stepper number 2, the pulse output or the step output is available on Q1 and Q2 for those 2 stepper functions. For direction, you'll want to use a general purpose output, one of the other solid state outputs to tell the motor or drive which direction to turn. Because the direction doesn't change very often, you can use just one of the standard solid state outputs, like somewhere between Q3 and Q12 for your direction output. Next, we check to see if we're ready to move. So if %I1617 is on, and if so, we can trigger the move by turning on Q1. After we've triggered Q1, we can check to see if %I1617 turns off. If it does, it means we're moving, and if at any point we see %I1618 on, we know we have an error. But if it remains off, then we're waiting for %I1617 to turn back on again, so we know that our move is complete. Let's look at a demo program for making all of this happen. So I'll open Cscape. Here is our standard program, and all this does is manipulate those digital bits. It tells you what the appropriate real-world registers are that you need to set for your parameters and which ones you need to monitor for status, and also the bit to initiate motion. To initiate a move, we decided to use a function key, and when that move is initiated, we turn on our start move bit, which is tied to Q1. Then we wait until the move ready done bit is off. When it is, we know a move is in progress. Then when we see that same status bit turned back on again, it means we're done and we can turn on another move complete bit, reset our move in progress internal status bit, and then reset our start move. So that's everything in this program for executing a single move. Next, we'll look at stringing together multiple moves. First, we need to create a user-defined function block that we can call to execute a move. In my UDFB, I want to be able to specify just the total distance in steps or pulses that I want to move my motor. Also, the UDFB should be waiting for a go signal to initiate the motion. Then it should complete the move and provide status telling us that the system has completed the move. So here's the variables that we'll put together for the UDFB on the input side. I'll have my go bit that initiates motion, an abort bit to stop things if necessary, and I'll have a move ready done bit that's tied to %I1617. For stepper number 1, I also need to monitor my move error bit, which is coming from %I1618, and I'll have a destination position that I'm going to feed the block. Then I also need to reference the number of accel pulses and the number of decel pulses because I need to provide that information to the OCS so we can execute the move properly. On the output side, I have to reference my step output, which if I reference directly is %Q1 for stepper number 1. I also have to reference my direction output. I could use Q3, Q4 or Q5 here for instance. Move complete will be an output of my stepper block, and then the number of running pulses will also be an output of my stepper block. That's because on the input side I'm determining whether the destination position is positive or negative. And if the destination position is positive, I'll travel one direction, and if it's negative, I'll travel the other direction. That just impacts my direction output bit. The number of pulses that I have for accel, decel and running is always a positive number, so there's some manipulation that will have to happen inside the UDFB. Keep in mind that UDFB variables that you create cannot be mapped to I/O points. The variables that are connected to them can be, but the internal variables for the UDFB cannot. Also keep in mind that you have to be careful with UDFBs if you have multiple instances manipulating the same output bit. And we have to be careful that those UDFB instances don't interfere with each other in regards to the stepper output. Now let's demonstrate that in Cscape. So first let's look at the UDFB that we created. This UDFB is doing more than our last program, so the first thing I'm doing in the UDFB is determining whether my move is in the positive direction or the negative direction. I'm doing that by checking if the destination position that comes in is greater than 0 or less than 0. If it's greater than 0, I'll turn on my direction output. If it's less than 0, I'll turn off my direction output. Next, I have inputs of destination position which could be provided as a positive or negative number. I also have provided to me the variables for the number of accel and decel pulses, which are always going to be positive. So as I need to calculate my number of running pulses, I need to make sure that I'm only dealing with a positive number for my destination position. If my move is positive, all I have to do is take my destination position and subtract off my accel pulses and my decel pulses, leaving the number of running pulses that the OCS needs to execute the move. However, if I'm moving in the negative direction, First, I need to multiply my destination position by -1 before I subtract off accel and decel pulses. This next portion of logic is identical to what we had in our previous example. When our go bit turns on, we set our step output, we check to see when the move is in progress, and then we check to see when the move is complete. I added this abort rung here so that if the abort input turns on, then I clear my stepper output. Let's look quickly at the variables that I have tied to this UDFB. This is my program variable window, and here is my step rail UDFB section. Here are all the variables that are tied to the UDFB. Here are my inputs, outputs, and then I have one internal variable. Again, we're not allowed to directly memory map UDFB variables. Any memory mapping we do is done on regular variables in the program. So elsewhere in this program, I have regular variables that are mapped directly to memory locations, and they will be tied to the UDFB. Now let's talk about stringing together moves in a sequence. Here we'll create an example that allows up to 8 sequential moves. We could easily do more, but we just set it up for 8 moves in this instance. Each move can be programmed for distance and direction, and each move can be programmed for a dwell time, so in between moves we can wait a certain amount of time before we move to the next one. We'll utilize arrays for our move parameters, so we'll have steps 0 through 7, and with each step there's a destination position and a dwell time. So let's demonstrate how you can create this example in Cscape. Here's some logic for sequencing these moves together. I wrote it in 2 different ways and both give the same result. In the first sequence I programmed, I used multiple instances of the stepper move UDFB. So every time I executed one of my up to 8 moves, I called a different instance of the UDFB. So this is the longest method because for every step we're in we have 4 rungs and we can have up to 8 steps. We start this off with a push button as long as we don't have a current move error and as long as we're not already executing the sequence. When we do that, we turn on a flag that says we're executing the sequence, and we turn on another flag that says we're on our first step, which we're calling step 0. Then we also trigger a go bit for the first step. We execute our stepper move UDFB, and that go bit that we turned on initiates the UDFB. The destination position we use is index 0 from our destination position array. Then we also have the number of accel and decel pulses that we're using for this move. Then on the output side of things, we have an output that will be mapped to Q1. That's our pulse train for the step to do the move. Then we have another output that will be mapped to our direction output to go either in a positive or negative direction. Then we have a move complete bit, and then we had to calculate our number of running pulses. So we execute this move with this UDFB, and once the move is complete, we then execute our dwell, and the amount of time we wait is based on the dwell value in the array of dwell times. Once that is complete, we check and see is this the last step or not. There were 8 steps in the sequence, but it's up to 8 steps, so you can configure less than 8 by setting a parameter that says what the last step is. It checks to see if the last step is configured as 0, because remember, we're on step 0. If it is, we clear our step flag for this step, and we clear our sequence flag because we're done. If it is not the last step and our dwell is complete, then we clear the current step and we set the next step and trigger for the next move. Then we'll use the same 4 rungs for the next step, which is step 1, and the other steps all the way up to step 7. Step 7 is different. Here we don't need to test and see if it's the last step because we know if we've gotten this far, it's the last step since it's the highest one we want to support. So after the dwell time is over, it immediately clears the step and the sequence. An important point is the outputs for step and direction for each UDFB are arrayed Boolean variables that are not themselves directly mapped to Q1 and Q3, which in my case what I use for direction. That's because of the fact that there are multiple instances of these UDFBs. If the Q1 variable was matched to each one of them, then they would conflict with each other, and the last UDFB in line would be the one that controls the output. That's not what we want, so instead I set up an array variable for step and direction for each of those UDFBs. And at the very end I have a rung for step and direction which makes sure that, for instance, When I'm in step 2, that it's only the step output from my UDFB for step number 2 that's being used to determine the state of my step output. This logic is needed because I have multiple instances and they're all potentially conflicting with each other when it comes to the step output. Next, let's look at the OCS. As stated here on this page, we'll be able to execute 8 moves and we'll be able to specify a dwell time at the end of each step. For the stepper motor I'm using, it's an integrated unit that supports 1600 pulses per revolution. Here, negative destination positions will move the motor clockwise and positive destination positions will move it counterclockwise. Here's what my trapezoidal move profile looks like. Of course, I need to set up the number of accel and decel pulses for each of my moves. In my application, I've left them the same for every move. The only thing that's changing on every move is the destination position, the total number of steps this moved, and the direction and the dwell time. I'm also leaving the starting and running velocities fixed. At 1600 pulses per second, this is basically 3 revolutions per second for my starting velocity and 5 revolutions per second for my running velocity. Let's set up our sequence. So on this screen, you can set for every step your destination as well as your dwell time. Positive numbers are going counterclockwise and negative numbers are going clockwise. I can also set what my last step number will be. If I want to run all 8 steps, I can use a 7 here. And then I can go to another screen I've created to monitor what's happening. I'll hit start and our sequence is now active. You can see we're stepping through from step 0 to step 7. And I have a piece of tape on the motor shaft to show the initial position. All these distances are done with even numbers of revolutions, so it should end up in the same location every time. You can see the dwell time is varying along with the distance and the direction traveled. We're stepping through from step 0 to step 7 because we executed all 7. I'll cut to the end of this now. If I want to make the last number 3, then I can go back, set my last step as 3, and when that's done, I'll go back in and hit start. And now I should go from step 0 to step 3, and then stop at that point because I'll be done with the sequence and my sequence active indicators should turn on after the step 3 dwell occurs. And you'll see that that worked. Going back to Cscape, now I want to show you a more efficient version of this same logic, which is another option. With this approach, instead of having 4 rungs per step, it's configured so it was just one sequence using one instance of the stepper remove UDFB. And I used indirect moves and a rotate instruction to keep track of what step I was on. Here again, I start off with a start push button, as long as there's no move error and we're not already executing the sequence. Then we set our current step to 0. With this approach, we keep track of what step I was on. I'm starting off with step 0, so after starting, I set my current step to 0, then I clear all of my other step flags except for step 0. I set my execute sequence flag, and off the end, there's also a start sequence positive transition to begin some indirect moves. These indirect moves are how we retrieve our destination position and our dwell times for the current move. Since we're starting with step 0, then we're pulling from the destination position array. The index for the array is handled with the current step variable, which is set to 0 when we start off our sequence, and then it will index through as we go, and then whatever destination position is needed for the current step gets copied into a different variable. Then we do the exact same thing with the dwell time. We pull from our dwell array using the current step index and copy it to a different variable. Then we have a go move positive transition that will be used to trigger our UDFB. I used an always on contact here, and here's my go move bit that is used to trigger the move. Our destination position comes in along with our accel pulses, decel pulses, etc. Because there was only one instance of the UDFB, there's no concern with any conflict on the output coils, so I could directly map my Q1 output and my Q3 direction output to the function block. Once we're done with this move for a given step, the move done bit turns on, causing us to start our dwell timer. When our dwell is done, we'll check to see if this is the last step. So is the current step equal to the last step? And if so, we'll clear all of our step flags as well as our execute flag. If not, then you move on to this logic, which says if this isn't the last step, I'll add 1 to my current step tally. Then I execute this rotate function. This takes these 8 step flags and it puts a 1 into the next one. So if I start out with a 1 in step 0 and I execute a rotate by 1 position for those 8 bits, then my 1 is going to be in step 1, and the next time I rotate it, it'll be in step 2, and so on. Then I trigger another positive transition, and we come back up again, pull out our destination and dwell times, and run through the loop again. So this method is a bit more efficient than the way I did it in my other program, but it will give me the same result. So that concludes our demonstration for today. Thank you for joining me for today's tutorial, and the Q&A session will begin shortly.
Okay, hopefully that was all very beneficial to you. I'm not seeing anything in just yet, so I will revert back to my screen. So next week is using Modbus TCP between OCS, followed by another Ethernet-based webinar with Ethernet IP, Modbus TCP, and EGD. All the registration links are there as usual. It's the same time every week if you want to get in for those. And again, all past webinars are always available. They're always uploaded within the day of it happening. Okay, I think that's it for today. Thank you all for joining us, and we hope to see you again next week.